So let me start by some comments that I wrote beforehand. So as usual, I'll try not to erase them, but if I am tempted to do so, please remind me. By mistake, I might take the eraser. But let me remind you of a couple of things that we have seen, and let's highlight, in the meantime, also a couple of comments that you can think of as just slightly different points of view. Of course, anyone can think in its own way, and it should all be fine. But I want to highlight a few comments and remind you of a few things that we have seen so far. Okay, so we started with the definition of a CFT by saying that a CFT is a theory for which, if we take the theory on a given spacetime or in a spacetime which differs by a Weyl transformation, we know how the two correlation functions are related. This is the definition, if you want, of a CFT, which implies that in flat space, in the same flat space, if you consider a correlation function of operators at positions x tilde, where x tilde and x are a conformal transformation, then the correlation functions of operator of x tilde and correlation functions of operators at points O are just related by a product of weights, omega of delta 1, omega of delta 2. Now, a first comment I want to make here, I just rewrote it slightly different. Normally I put tildes on the left-hand side and not tildes on the right-hand side. And omegas, I always put a minus sign. Remember, it's omega to the minus delta always. So I just put omegas on the other side, and it's a number. I put it inside the expectation value, and I group them in this way. Okay? Nothing special here. Right? It's just you can remove all the omegas from this expectation value and put it on the other side, and this is the formula we had been writing. Okay? Just now, I want to adapt a point of view where we will try to ask ourselves what happens to an operator under a dilatation. We saw how the conformal group acts on points. This was the goal of the exercise. We translate points, we make a dilatation. What is the representation of the conformal group on operators? So then what we will do is identify this guy as our transformed operator. But let's do it in a moment. For now, it is just a recap of what we have seen before in a slightly different notation. We also saw that correlation functions in the cylinder, for this tau and tau prime in the cylinder, so we had our theory on R times the sphere, and we have some tau here, some tau prime here, and we have some operator and some operator. They are at different positions, means that the different unit vector n that parameterizes the points in the sphere. So where are they pointing? And the correlation function for a CFT on the sphere was only a function of the difference, and it smelled like these deltas should be somehow related to some energies. This we could see, for example, because we got the typical behavior that we expect for some system where we separate it a lot and it evolves in time. Okay, then we also saw that conformal symmetry was extremely powerful in constraining the form of 2 and 3 point and 2 and 3 point functions, and to some extent also 4 point functions. And in particular, I said that you can always choose a base where the correlation function between two operators is 0 unless the operators have the same dimension, and then you can furthermore choose a base where the operators are orthonormal. So two operators, the correlation function is delta ij unless they are the same operator. Sometimes, okay, if the theory has complex fields, maybe this is ODEG or something like this. And there is some delta ij, otherwise it is 0. Now, of course, if you give me this equation, if you choose to use fields which are twice as big as my fields, you get the 4 here. And that's not really physical, that's just a field redefinition. And you can just, I can work with phi, you can work with 5 phi, I can work with 1 over square root of 2 times phi, it's your choice. So of course, in general, well, let's do it here. We can say that we have some arbitrary normalization ni. And if we change the normalization, the 3-point function will also change by square root of ni, nj, I'm not very good at drawing curly, and nk. So I just want to emphasize the obvious thing that, or I want to emphasize that these guys are unphysical. It's just my choice. If you give me some operators, of course, I can define a normalized operator. But you see that this C is invariant on the normalization. That is, if you give me some operators, I compute a 2-point function, I find n, and then what I read is this C by computing the 3-point function and dividing by the square root of the normalization. Okay? So this guy is physical. It's what measures the interaction between 3 operators. By unphysical, I mean that you can always normalize the operators to 1. You are not obliged to do so. Of course, there's nothing physical in saying that I choose a normalization where the operators are normalized to 1. Any normalization is equally good. It's not that one is more physical than the other. But because you have this freedom, you can say, what is the 3-point function? The 3-point function, you have two options. One is to say that, okay, it's what appears when I write the 2 and 3-point functions in this way. Another way of saying is, once I fix a normalization such that the 2-point function is 1, C is physical and it is what measures the interaction. Okay, just some obvious comment about normalization. Then we saw that for 4-point function, conformal symmetry was not so constraining. So this is a function of two so-called cross ratios. If you put this function to be 1, this transforms under inversions as it should. But for any function f, it also does because these cross ratios are invariant under inversion. So these cross ratios was just, here I wrote it graphically. For example, u is the distance between 1 and 2 squared times the distance between 3 and 4 divided by the distance between 1 and 3 and the distance between 2 and 4 and similar for v. So these are ratios of distances that become 0 and infinity when you take particular degenerate limits. I want to make 3 more comments before we move to the lecture itself. Yes?
Can I ask you something about this? In the second line there,
yes.
Do you really mean that x1 tilde is only a function of x1, for example?
Yes. So x1 tilde is, for example, so let's see here. For example, under inversions. Under inversions, x tilde mu is just x mu over x squared. So x tilde mu for 1 is just for example, under an inversion.
Oh, sorry, I was okay. Yes.
Very good. So 3 more basic comments. Okay, 2 are very basic and 1 is slightly deep. So one comment is that we have some algebra, and here are 3 of the commutation relations. Okay? K with P gives dilatation and rotation, and dilatations, P and K transform under dilatations in this way. The second comment is that special conformal transformations in its finite form are described by this. Remember, this is an inversion, you translate and you invert back, and this is the final result. Finally, the last comment, let me just remind you that in quantum field theory, when you compute, what does the path integral compute when you compute averages? It computes the time-ordered average of fields. Okay? This is just a statement that you are familiar with. It has nothing to do with our lectures. There's a statement that in a quantum field theory, the time-ordered product of O as an operator. So if you compute operator at time t1, operator at time t2, it can depend on other labels like space labels or whatever. And you compute this is what the path integral computes. You put the field O at tau 1, the field O at tau 2, it's computing this time-ordered product. Okay? So this, when we say expectation value on a theory that has time times something, what we mean is, of course, in the language of canonical quantization, the time-ordered product of the operators corresponding to the fields that we are computing the average of. Yes?
Can I ask you that? Was there like a correction on the commutation relation from before?
K and P?
Yeah, it's slightly different.
There is a minus maybe?
Like there's an I, yeah, and there's a minus difference.
No, there should always be I. So if there was not an I before, it was a typo.
There isn't an I here.
Sorry?
There is no I here.
There's no I?
DP? No.
No? Where is it? No. Here, no. Of course, this is a typo, yeah.
Oh. Yeah, so the second thing is, so for the 4-point function there,
yes,
you chose a specific one where the operator is the same one.
That's right.
Okay.
The operators are all the same. That's why they have no label here.
Okay.
So here they have a Y and a J, and this was the case where all deltas are the same. Yeah, this I mentioned in the last lecture.
Okay.
Okay? All delta I are the same. It's very straightforward to generalize when they are different. You just come up with a different factor here that scales in an appropriate way. If you want, I can do it.
No, I mean, do you mean it's they can be different operators with the same delta I, or they have to be the same operators?
No, they can be different operators with the same delta I. But for the case that I'm considering, I wrote it as if they were the same operator, right? I used the same letter O for it. What I wrote was for the same operator, but actually it is true if they are different, but with the same dimension. Okay, so what we can write, one way we can write this relation So any questions? Otherwise, more questions, please. Yes.
Would you mind explaining that n again?
That what?
That n, ni, and root ni, and j. What does that mean?
It's a non-physical normalization. So if you use an operator, suppose you have some theory like a free scalar, and you choose to consider an operator, a composite operator, say phi square of x. But phi square of x, when I compute two-point function, probably there are two diagrams, it gives 2 over this. Does it mean it's a bad operator? No, it's okay, just put a 2 here. Doesn't matter. You could, of course, define the operator 1 over square root of 2 times phi squared. That would have two-point function 1, but that doesn't make it a more physical operator, it's just a normalization. But if you use that normalization where you get a 2 here, then here you will get an 8 or something like this. And the invariant quantity, the quantity that doesn't change when you rescale operators, is obtained, is this C here. Okay? So if here I'm getting 4, here I should divide whatever I get by the 3-point function by square root of 4 times 4 times 4 times 4, which is probably 8, and then you get the 3-point function. Is it clear? I could say it in another way. I could say that the physical object, I can construct an object that is invariant under normalization. I just multiply this guy by a bunch of 2-point functions up and down, such that the dependence on the normalization of the operator is obviously not there. And then you can see that that object is given directly by C. I can construct, I mean, if I try to do it, I'll get it wrong, but I can try. Should I try? I'll try, but it will not work. Let's try. Okay, good. So now what I want to do is divide by stuff, which is OI of X, OJ, OI, of Y, and I could consider also OI of X, OI of Z. Okay. And now let's see. So this guy is some normalization n I divided by x minus y to the power 2 delta. And this is some normalization ni divided by x minus z to the power 2 delta. Right? Good. So, 1 second. Yes. Okay, great. So, if I want to consider something like this, 1 over x minus y to the power delta I plus delta j minus delta k, what is it? Okay. So you see that I can get x minus y to the power delta y from this guy. I can get x minus y to the power delta j from a similar guy with j, and to delta k with a similar guy with k. So I can write this up to a normalization. Okay, let me write proportional to square root of OI of x, OI of y times OI of OJ of x, OJ of y divided by the 2-point function OK of x, OK of y. Is it clear? So if I do this, then I reproduce this dependence, but some n's remain. So then if this guy is given by this, so what should I do here? I should divide each guy by the normalization. So then I also have square root of some normalizations that appear, which is something like, if I do no mistake, nk over ni nj. Okay? Is it clear? So if I multiply 3 similar guys like this, at the end I get just square root of ni, nj, and k, you can check. And therefore what you can conclude is that if you divide this by the square root of one guy like this, another one, a similar one, and a similar one for the 3 denominators that appear in the 3-point function, So this is one of them, this is another, this is another. See? Then it is clear that this object has no space dependence, right? Because by construction we divided with things that are meant to cancel the space dependence. But if you are careful, you can also see, let's just try, without ignoring the, let's try, hopefully it will work. So here we have OI square, OJ square divided by OK square. So by square, I just mean I'm just counting how many powers of O there are so that I can see if it's invariant under normalization or not. And now let's see. When OI is rescaled, this is 1 power upstairs, but there is 1 power, 2 powers, but 1 power downstairs. So this is also invariant under normalization. Okay? So it's easy to see that this is nothing but the 3-point function Ci(j)k. This is one way of defining a ratio of correlation functions that by construction gives you the structure constant and nothing else, and it's invariant under normalization. Okay? Of course, it's never the way you compute it. You write the 3-point function, you see the normalization of the 2-point function, and you divide by it to read it out. Okay, very good. Now, more questions. Wow, we are already 20 minutes. More questions. Okay, so let me just point out that I can, of course, interpret this equation as saying that I have my operator O at x1. I can define, just for my notation's sake, this guy as being what I mean by a transformed operator O tilde. And I can define this to be my transformed operator O tilde at xn. Okay? So a theory being conformal invariant, so conformal invariant, I can write an equation that looks like a conformal invariance. Is the statement that if I have operator x1, operator xn, this is minus the same thing with tildes, is equal to 0. Okay? Again, let me emphasize, this is a definition. Okay, so this is a statement of conformal invariance. If my operators transform according to that rule, then correlation functions are invariant under this theory. So how did they transform? So O tilde of x minus O of x. Let's see what it is, say, for an infinitesimal dilatation. Well, for a dilatation, that factor omega for an infinitesimal one is just lambda, so it is just 1 plus epsilon to the power delta. Then we have operator at the point x tilde, which is 1 plus epsilon times the point x, minus the operator at x, which is just equal to epsilon, so it's infinitesimal, it's very small, and then delta plus x d dx acting on the operator. So then, the way we can write it is that under a dilatation transformation, the operator O at a given point x transforms. And okay, remember that momentum, what translates is not P, it's IP. So there are a bunch of I's when you put transformation for the generators. You would say that this is equal, let me try to put the I, the correct I, minus I delta plus x d dx acting on operator x. And in particular, a way an operator at the origin transforms is just minus I delta times the operator at the origin. Okay, very good. So this would be how an operator transforms. And we could repeat it for all other fields at the origin. So let me still write it here. Delta D O is equal minus I delta O. So all this will be at the origin. I will write in a minute. What about M? M would not change because it's a scalar, so it will not rotate at all. What about P? P, it would be just some derivative. And what about K? Well, the transformation of K, the infinitesimal transformation, you can think it's a small translation, but it's a translation that if x is 0, it doesn't translate at all. You see, if you put x equal to 0, infinitesimal, it does nothing. So an operator at the origin is killed by special conformal transformation. So all this is at the origin. So it's for an operator inserted at the origin with a given dimension delta. Okay, very good. Now, of course, these guys are also operators. I mean, here we are treating them as fields. So all this is equivalent. So this is as fields, as operators. I can, of course, write all these equations as just saying that D with O is minus I delta O, etc. Okay, in the usual canonical language. Okay, so if you want, this was just a summary and rewriting of things that we knew already. So, I mean, conceptually, I don't think there's probably anything new in this Blackboard, except maybe emphasizing this normalization and reminding you of this time-ordered stuff. Okay, so finally, let's start to study some new stuff, and in particular, something extremely important, which is called the state operator correspondence. Okay. So let me remind you that the metric of something, that the metric in flat space as we saw several times, it can be written, it's conformally flat space, it's conformally flat to a cylinder. Under just that, under identifying R to be to the tau. And this leads to a picture of radial evolution, where if you have your radius that is increasing, so here is some different radius. So these guys here are spheres, some radial coordinates. When you have some spheres, this would be R equals 0, this would be some R, this would be some R prime. In terms of the cylinder, what we have is we have a cylinder and we have some tau and some tau prime. So tau prime is bigger in this picture, so I put it up. And that's it. And correlation functions of operators that we put here, O tau 1, O tau n, O tau and tau prime and prime, as I was reminding you before, should be thought of as a time-ordered product of expectation value of the time-ordered product of the operators. Where now we are thinking in terms of the theory on R times S3 as being just usual quantum mechanics. Quantum field theory is also quantum mechanics, so you have some time evolution. And this, by these operators, I mean the usual Heisenberg operators. So this is just E to the tau times the Hamiltonian that evolves time in the cylinder. Operator O inserted at 0 and n, where this O is Schrödinger, this is Heisenberg, the usual stuff. So this is Heisenberg, this is Schrödinger picture. E to the minus tau times Hamiltonian in the cylinder. Okay. So this is not anything special, as we said. Conformal field theories are also quantum field theories. It's always the usual rules of the game. Okay, so now, it's a pity I didn't have enough space in this picture, but let me try down here. Okay, so now comes the important simple observation. So the first observation that we make is that the dilatation operator here should be related. Okay, I could put an equal sign, but let me put these arrows. But these arrows could be an equal sign, but let me explain why I'm putting arrows. This dilatation, so dilatation in R, what does it mean? R goes to lambda R, means making a translation in time. So a dilatation in time is equivalent to the Hamiltonian in the cylinder. Is it clear? Now, why did I put this in? Because of course, this is Euclidean, and if I want to be strictly speaking the Hamiltonian, I should put an I here and an I here. And if I put an equal sign, there's a probability 1/2 of getting the sign wrong. So I put an equal. Okay? You understand? So I mean, of course, they are literally the same operator, up to an I. So this immediately implies something important, which is that the spectrum of dimensions in the theory in RD is nothing but the spectrum of energies for the theory in the cylinder. Okay, and here is a particular example where we see that the deltas, indeed the energy and delta, this formula matches our expectation if we think in those terms. Very importantly, what does it mean to put an operator? Suppose we put an operator here at the origin. So by this yellow line, I mean there is an operator. And suppose there is another operator here, another operator here. So let's first draw the other two operators. One is here, and the other is here. Now, what does it mean to put an operator at the origin, O at 0? To put an operator at the origin means to specify your boundary conditions for your path integral close to the origin. That's the definition of a local operator. Okay. In other words, you can think that you are doing your path integral, you put your point O at the origin, and then imagine you do a bit of path integral radially away from the origin up to a circle of length epsilon. And then you get a functional of your field at that sphere of epsilon. That is what the functional is because you put a local operator there. So in other words, you are telling how your fields behave very close to that point, and you can shrink it as much as you want. Okay? When you are doing this kind of pathing. So putting an operator O at the origin, so an operator at the origin, is equivalent to choosing boundary conditions at the origin for your path integral. Very good. What does it correspond to put an operator at the origin here? Here, it would correspond to our choice of initial wave function. So an operator O at the origin can be thought of as creating some wave function in the infinite past, just by this conformal map. Okay? You could also think even here radially. You have some operator, you make a small sphere around it, you have some wave functional, so you are defining a state around that point. So you have this map that working with operators or working with states, it's exactly the same thing. If you want to be even more explicitly, suppose you have this operator here, suppose it's one of those operators here. What is happening? You are sending this tau to minus infinity. So you have this operator O, and you are sending this tau to minus infinity. Right? If you are sending it to minus infinity, you can take it out of the time order. You are sure that this is the first guy, and you can make it act directly on the cat. Acting on the cat, it defines some state. That state is what we call O. Okay? Let me repeat again, some of you might be copying. I have some operator O, and if I take this tau prime to minus infinity, we can take it out of time order. And then we define the limit of this operator when tau goes to infinity and so on, times the vacuum, to be our definition of the state O. Okay? Let me see if there is something else that I should add. So, so there is this notion where we specify, if you want, the initial wave functions here. So this is our analog of considering cats. Here it will be the analog of considering a bra. And we can do just usual quantum mechanics where states evolve in time, and operators are in direct correspondence to states in the theory in the cylinder. Okay? Is it okay? Just usual. So at any sphere that you have, the way to think about it is that at any sphere that we have, say we have a sphere here, for example, what is this sphere mapped to? It's mapped to some circle here. And at this point, we have here some state psi in the cylinder. What is this state psi? It's the state that I get by starting with O and acting with O, which is what I get by starting with this operator here and acting on it on the state O. And then I continue evolving and I get my state until I overlap it again at the infinity. So there is this notion that evolution in time in the cylinder is the same as evolution in the radius in the original theory, and this is what is called radial quantization or radial evolution. Very good. Again, the main principle is the idea that doing the path integral on a sphere, on everything that is inside a sphere, is basically defining for you the functional of fields on that sphere, which is nothing but a wave function, which is nothing but a state. Okay? It's just that. So if you do path integral up to a given sphere and say that on that sphere my field is given by some value phi, what you are computing is the wave functional of that field phi, which is nothing but a state. Okay? Yes.
So just a confirmation. So on the left hand side, when you are still in the plane, and that O is the denotation operator.
That O is any operator, a local operator. No, it's a local operator.
So when you are saying that you act O on the initial state,
Yes.
and then you get the evolution, and that, I suppose, does that mean that the O is like some evolution?
No, O is any operator. You just act with a vacuum on any operator. Like in the harmonic oscillator, you act with your operator with some creation operators or annihilation operators or whatever you want. Any operator. So take a very complicated operator, which is a linear combination of many creation and annihilation operator and so on. It's a big monster. Act with it on the cat zero. You get something, that something is the state. Right? O is an operator. So let's understand a bit better the dictionary. So here on the left, let me maybe copy it again. We have acting on operators. We have this statement that I can write it in any way. Maybe this is more familiar. This okay, very good. So what does it translate to? What's the analog in the cylinder? Well, it is just that you have an operator D that acts on the cat O and gives minus I delta O. You have a rotation generator. Your state is invariant under that. You have some operator K that kills your state. And you have P mu acting on O that is not 0, and that generates, if you want, another state. Okay? And you generate another state, so you have your state O, and you get other states by acting with this P. So P mu acting on O, P mu acting on O, and so on. So it's just, in the original language, derivatives of your original state. It's a cheap way of getting new operators. You have an operator, consider the derivative of that operator, that's a new operator. It's a very simple way of getting new operators. Just take derivatives of it. So these guys here are what are called descendants. And this guy is what is called the primary. Now, you can and you should complain that I promised that at some point I would explain what was this notation for primary, what was a primary, and now not only I'm not explaining, but I'm introducing new notation distinguishing a primary, which is an operator that is killed by K, from the descendants, which are the states that you get acting by P, but I will ratify that in a minute. Let me finally mention that if you want to define, if you want to consider spaces of theories that after going to the cylinder, they are unitary. Maybe you don't want to, but if you want to consider unitary theories are theories for which you start here, you go to this picture and you get a unitary theory with a unitary Hamiltonian and so on. So if you want unitarity, an immediate thing that we get is that the dimensions are real numbers. I must emphasize that not always we want unitarity. In statistical physics, often we deal with models that are not unitary and they're also fine and also useful. But if we have unitary, the spectrum of energies should be real, which means that the spectrum of dimensions should be real. Okay, very good. So now, we will now understand why it is very important to have this class of operators that are killed by K and that are not killed by P. So we can think of K as being an annihilation operator that kills the state, and P as being a creation operator that generates your Fock space in your cylinder. So it's really exactly what it is. So this is generating a Fock space in your cylinder of the states. You start from O and you act with P many times as a creation operator and you create many states on your cylinder. Okay, but related a bit to unitarity, I want, before explaining a bit where does this come from and why this is roughly the only thing, why this is roughly imposed on us by wanting a physical theory, let's just consider something important, which is conjugation of operators. So what is the Hermitian conjugate of this operator? Okay? So of course, once you have some operators, you can ask what is the Hermitian conjugate, and you can work it out by just working out the action of the fields and seeing what it is by acting on functions. But it's easy to see what it should be. So what does it mean to have this dagger? Dagger means that it also either acts on cats or it acts on brass. So if you have a dilatation, the dilatation is naturally acting on the cats as a dilatation. Acting on at infinity, it is doing the opposite, right? Because infinity and zero are related by an inversion. So if something is becoming more separated close to the origin, it's becoming more squeezed when you do x1 over x. So the dagger is, and indeed you can check, minus d. Okay? M dagger rotating points rotates both 0 and infinity, so M dagger is just equal to M. What about P dagger and K dagger? Can someone make a guess? Sorry? So the guess is that P dagger is P? Okay, other guesses? So again, what we should think is, if P acts in some way close to infinity, close to 0, how to relate to what it should do close to infinity? So what does it do at infinity? But remember, we said that P and K are related exactly. One is nothing but the other if you do an inversion. Right? So K was exactly, so actually the correct answer is that the Hermitian conjugate of P, making a translation close to the origin, is nothing but K. Because the definition of, if you want, in this picture, the fact that operators act on cats and brass translates into this state. Okay? And indeed, if you put here P, or if you put here, okay, you can multiply by I and put I, J, I. If you put I, P, I, this is exactly what K was. Okay? So it's just a statement that K, we define that. Do an inversion, so go from cat to bra, translate, and translate. So K is a translation after doing an inversion, after exchanging cats and bra. Okay, very good. Oh, this was one comment, this was another comment. And once you have some operators that you know their algebra, you can ask, so what is the representation of these operators? And of course, we already started answering this question because we already wrote down what the action on the states is. But let's see that it could not be anything else. And for that, it is very useful to use the relation up there that tells us that, sorry, one second, let me. It's very useful to remind ourselves that D with K mu is equal to I K mu, and D with P mu is equal to minus I P mu. As you pointed out, I had a typo in the beginning. Very good. So this means, so what we are going to do is the usual story that we do in harmonic oscillation. We show that if some state has some energy, or the A dagger times that state has energy by 1 unit more, just by using the commutation relation. So maybe, okay, let me still do it even though it's more or less simple. So then we conclude that let's compute what's the dimension of a state K mu acting on O, on the state K mu acting on any state, Or this psi has some dimension delta. Well, this I can write, it is just the commutator of D with K mu plus K mu D acting on psi. I did nothing. And this is just equal to, the commutator is K mu with some I. D acting on the state is minus I K mu times delta, because remember D was giving minus I delta on the state, which is equal to minus I times delta minus 1 acting on K mu times psi. So we conclude that this state has dimension delta minus 1. Okay? So that means that if we want to have a spectrum that is bounded from below, if we want the dimensions not to go down forever, K must kill some operator at some point. Otherwise, we will have dimensions going all the way to all negative numbers. Yeah? Is it clear? So unless K kills the states, we have delta will not be bounded. So bounded, we want the spectrum, bounded spectrum of delta, implies that there ought to exist highest weight states such that K acting on those states is equal to 0. It ought to be, there ought to be some states where it is 0. This is the definition of a primary, if you want. So a primary is defined as the highest weight where things stop. So this psi was an arbitrary state somewhere in the Hilbert space. And I said that psi, any state in the Hilbert space, if I apply K several times, I reduce its dimension. At some point it must stop, and when it stops, this is when we arrive at the primary. Is it clear? Okay, so we have a primary. Such that it's annihilated by any special conformal transformation. And then P mu O, P mu, P nu O, etc. are descendants, are called descendants. And what is their energies? What is the energy of these states? Yeah, exactly. They are shifted exactly like the harmonic oscillator. So this has dimension delta plus 1, delta plus 2, and so on. So the spectrum of conformal field theories is that we have some primaries that can have some dimension delta, which is not necessarily an integer. It can be whatever you want, pi square, whatever. And then a bunch of states whose dimension is just shifted by the dimension of the primary by integers. So the dimension acting, say, on P mu, acting on some O, is equal minus I delta plus 1 acting on that state P mu O. Very good. Now, important to emphasize, from the very beginning, we were considering always correlation functions of primaries. Okay? So we were always considering correlation functions of primaries. If you know a correlation function of a primary, is it easy to get a correlation function of a descendant? This is the question. Yes, descendants are just derivatives of a primary. So of course, if you know a correlation function of a primary, a correlation function, say, of a descendant, it's immediate to obtain. So correlation function of, say, a descendant, so this is d mu O at position x1, OI, OJ at x2, OK at x3. Can you read? It is just equal to the derivative with respect to the x1 of the correlation function of the primary. So of course, if I know one, I know the other. So the interesting ones are the primaries. Those are the ones we need to compute. The other ones, they are just obtained by acting trivially with creation operators, which are these derivatives, that increase the dimension by 1, which is natural. A derivative has 1 unit of mass. And that can be obtained trivially from those of the primaries. Yes, there was a question.
Sorry. How do we know that the formula is true for the Hermitian conjugate? J equals inversion J dagger I?
If you want, this is the action. This is the definition of dagger. Dagger is defined. You have a cat at 0, an operator at infinity. How do you relate the two? By inversion. I mean, this is roughly the definition of what Hermitian means. Maybe what you want is the following. Okay, maybe let me try to write something. Maybe will make you slightly happier. So if we went to the cylinder, and if we rotate, we go to the cylinder, and we weak rotate to have a Lorentzian theory, then unitarity should be the statement that a dagger of T in Lorentzian, so this is for Euclidean. Euclidean. In Lorentzian fields, it should just be the statement that the operators are the same, because they are observables. Okay? So this implies that the operators in Euclidean, in tau, are related to each other by tau to minus tau. But a of minus tau, what is a of minus tau? How do we change tau to minus tau? Well, tau equals 0 is r equal 1 is the unit sphere, and we change it precisely by an inversion. To change tau and minus tau. And if you want to go back to those formulas, you just set tau equals 0, and they imply the formulas written here. Okay. Very good. This is a parenthesis. I don't think it is needed for the logic, but it might help. Very good. Okay, so please tell me of your concerns. So any questions here? Let me tell you, maybe let me anticipate something that I will tell you tomorrow, so that you can have an idea of why this can be extremely powerful. Why could this be something very interesting to do? Why are we doing this? Okay? So there are several things. So one reason is that right now, in the remaining 5-10 minutes, I'm going to show you that this point of view immediately implies bounds on the dimensions of these operators. Just because we have some states, the norm should be positive, and immediately when we start playing this game, we'll get bounds on the norm of the on the dimension of the operator. That's already one nice outcome. But the most powerful one comes from the notion that if you have some state here, psi in blue, the state in blue there, the state can be decomposed in all states of the Hilbert space. It's one state in the Hilbert space, it can be decomposed in the states of the Hilbert space. That has an interpretation because each state in the Hilbert space is an operator. So that means that if you consider a bunch of operators inside a sphere, you can replace them by a sum of operators inserted at the origin. Because it can be understood as some state psi, which is a sum of operators that I can always consider as inserted at minus infinity. So that will immediately mean that if I have some operators inside a sphere, I can replace them by a sum of infinitely many operators, but inserted at the origin. I mean, this is natural. You are just saying, I have a bunch of operators inside a sphere. I go to Boston and I look at them. Of course, they look like one operator plus a multipole plus quadrupole and so on. It's very natural. But this is proving it. So it is really making it, it tells you what's the radius of convergence. It will tell you a lot. And that notion of replacing operators inside a sphere by operators inserted at the origin, as you see from very far away, it's an extremely very powerful point of view because it replaces many points inside the sphere by just one point at the origin. So by doing this kind of trick, when we have a correlation function of many operators, we can isolate operators around spheres, put two operators in a 4-point function around a sphere, two operators around another sphere, do this game and reduce the 4-point function to a 2-point function. And that is why this kind of game will be very powerful, and in particular we will see that it will allow us to determine completely all correlation functions of our theory in terms of what we call the CFT data, which was the dimensions in the 3-point function. Okay? So the goal was not for you to understand all the words I just said, but to get a picture of why going in this direction is extremely promising. Okay? Is it okay? But did you get more or less the picture? Yeah, okay, let's go on then to some slightly less ambitious things and understand something about bounds, about unitarity bounds. I understand that I'm probably very bad at putting titles. I never do this kind of thing of putting titles. You should tell me, to remind me to do so. There's almost no titles here, but okay. So unitarity bounds. Unitarity bounds is the statement that these dimensions must be bounded because of unitarity. So one constraint of unitarity is that the dimensions live in R. But let's see that it's very easy to get more constraints. Suppose I impose that I take a state that is C mu times P mu acting on some operator O, some descendant, and I impose that the norm of this state must be bigger or equal to 0. That's the norm. Now, what does it imply? It implies that C mu conjugate times C nu, so I'm writing this, it will be times O times K mu P mu O is bigger or equal to 0. Okay. Is this obvious? I just used mu and u not to use the same index, and the conjugate of P is K, so that is exactly equivalent to that condition. Is it clear? Now, because K kills the operator O, I can replace these guys without doing any approximation. I can just add a commutator here. Just because K kills the vector. Is it also good? And then I can use the commutation relation that I have at the very top to replace this by 2I delta times delta mu nu plus 2I n mu nu. And I can use the fact that m kills scalars because scalars don't rotate. So all that matters is this d. Okay. Can you read if I write here, or should I move somewhere else? You cannot read? So then what we get is C mu dagger delta mu nu I O d or 2I O d O bigger or equal than 0. But this thing here was minus I delta times O with O. This here is just absolute value of C mu squared, which is by definition, which is of course a norm, so it's bigger than 0. So then we conclude that delta must be bigger or equal to 0. It's already nice. Is it clear? Okay. Next, we could do another exercise. Wow, I must hurry. Okay. And then we can do another exercise, which is to compute, for example, what is the norm of P mu acting on O. Okay. So, is it clear what you would do? Right, P, like K, P, start commuting the K, then commute the P and so on, and work out of this case. Do you allow me not to do it? Is it clear conceptually what you would do? It's exactly a generalization of what we did, but just it has 2 Ks and 2 Ps. It's like we have to commute it twice. Is it okay? What we get is that this becomes, so the left hand side, I'll write what you get so that you can check. You get A8 delta D delta minus D minus 2 over 2 times O bigger or equal than 0. So you conclude something interesting, something stronger than this. You conclude that either delta is equal to 0 or delta is bigger or equal than D minus 2 over 2. Delta equal to 0 can appear, but it's a trivial operator. It's the identity operator. Okay? You agree that correlation function of 1 with 1 is 1 over x minus y to the 0. Okay? Very good. And this here is what is called the scalar unitarity bound. And there are similar bounds for operator with spin. So for operators with spin L, you have similar bounds, delta bigger or equal to D minus 2 plus L, if I remember correctly. Okay, which you could do working out generators with spin, which you would work out in a very similar way, except that this generator M does not kill operators with spin, but instead rotates them, and you work out the representations of SOD and so on. Conceptually, it's not more complicated. Technically, it is. Okay, and you also see that if delta, this is not much bigger, of course. Bigger already. If delta is equal to d minus 2, if it is equal, if it saturates the bound, then it means that the norm is 0, right? Furthermore, we see that if delta saturates the bound, it means that the norm is 0, so it means that p mu O equal to 0. This is nothing but the Klein-Gordon operator box. This is telling you that O is a free scalar. So for a free scalar, and only for a free scalar, you can have a bound being saturated. So if you have a free theory, it is saturating the bound, otherwise it is bigger, strictly bigger. Very good. Now you can ask, well, but this was a dangerous game. I started playing the game with just p mu, I got one bound. Then I did with p mu square, I got a better bound. Right? Looks a bit dangerous. What about starting with 3p's and 4p's and so on? Well, it can be shown, but it's actually hard that this is the best bound you can get. You cannot get better stuff by considering more complicated operators. But this, to my knowledge, I actually don't know how to show it. I know it's possible to show, but I think it's something hard. I don't know if someone has any comment. Do you know that, Emil?
Well, you need to consider the matrix of the at the nth level and to calculate its determinant.
You mean for d dimensions? For 2 dimensions, you mean?
No, in arbitrary number of dimensions. And
okay. I know Minwala tries to argue that, but I don't know. I mean, okay. If you want, you can explain.
It's very difficult.
Yeah, I also think so, but I never thought about it. Okay. Very good. And now the time is over, and I have to go a bit over time, because otherwise the tutorial will come out of the sky and you will not understand what is at all written there. So I need to spend 10 minutes explaining what the tutorial is about. But it's very important. I mean, any questions so far? So far we see that the spectrum of CFT is not whatever we want. There are bounds on it. Is this like this or like? Which way should I use? Oh. Okay. So let's just have some appetizer into ADS here. By the way, let me say something. Let's consider the tutorial prime to be establishing this relation. For those that want to play more with conformal algebra, this is something useful, so let this be an exercise if you want to play more with conformal algebra instead of doing something completely different. If you want to get more familiar with this algebra, this might be a more useful exercise. Very good. So we started with RD, which was just dx mu dx mu. Now, one thing we could ask, and again, this is just, I will hand wave for a while just to motivate a few metrics. You could ask how to make a spacetime that is invariant under dilatation. Yeah? Now, this spacetime is not, I do a dilatation, it goes to lambda times itself. So what could I do? Well, I could introduce another coordinate z squared that also scales such that under dilatation, I scale x and I scale z, and this is invariant. Of course, if I introduce a new coordinate, now I'm describing a spacetime with one more dimension, and I must do something with it. And if I want to preserve scaling invariance, this is what I should write. So this is a spacetime that has scale invariance. This is a spacetime with scale invariance. So z goes to lambda z and x goes to lambda x is a symmetry of this spacetime. But actually, there's something even more interesting about this spacetime. It is invariant under some funnier transformations, where x mu goes to and notice while I write how similar it is to the special conformal transformation there. So what I'm writing is an isometry of this spacetime. So some transformation that leaves the metric invariant, not of 12, really invariant. And x mu goes to x mu. I can really copy it completely. It will not be the end of the story, but almost. But let me just copy it. By the way, there it was not. Okay. But this way. Okay. And all we do in the spacetime for this to be an isometry is we add plus z square plus z square. Sorry. So up there was an x squared. Sorry. So there is an isometry, and Z also transforms in a simple way. And what is fun is that as you go to the boundary of this spacetime, so this is a spacetime that when Z, that you can think that it's like a foliation. So for different Z's, you have different, so if this is Z, for different Z's, you have different copies of Minkowski with a different scale factor multiplying it. And you can think this is Z equals 0, which is the boundary of the spacetime. So this is a spacetime which is defined in a semi-line times Rd. This is the topology of the spacetime. Z equals 0 is the boundary. And then you have copies of Minkowski as you go inside, or of Rd. And close to Z equals 0, these isometries become nothing but the conformal transformations of points in the boundary. In the boundary of this spacetime. And this spacetime is what is called anti-de Sitter. This is what is called anti-de Sitter space. Anti-de Sitter in one bigger dimension than the space we consider in, where this here is Rd. So this is the most natural space that becomes scale invariant. To make it scale invariant, you introduce some extra direction. And then, once you introduce this spacetime, the ADS-CFT conjecture tells you that if you consider correlation functions of operators in your boundary, say a 3-point function like the one you compute. So if you want to compute 3-point functions, what you do is study string theory in this curved spacetime and study a path integral over all strings that end on these points with particular boundary conditions. As we said, operators specify boundary conditions. So here we have what is called the boundary, which is where the CFT lives. And here we have the bulk, where string theory lives. And the statements that the two computations gives the same is the statement of ADS-CFT. And of course, I'm not proving, I'm announcing it. And I want to tell you that, of course, the conformal field theory, you can consider it on the plane, but we saw that it's also very natural to consider the conformal field theory on a cylinder, where this is tau, and there are points n unit vectors which parameterize a sphere. This picture is even more suggestive because when we think of a cylinder, we want to fill it in with something. And this something is exactly ADS. So another representation of the same spacetime is that another metric of ADS, other coordinates of ADS, are given by the following. This is what's called ADS in global coordinates. And as rho goes to infinity, rho is a radial coordinate, is what measures how far away you are from the center. And t is this tau here. Okay, we can call it tau. It goes to e to the minus 2 rho times, if we consider a very large rho, d tau squared plus d omega squared at d minus 1, which is nothing but r times the sphere. And the conjecture is again very simple. You consider correlation function of your operators on the boundary of this spacetime, and you can do it, you can compute them alternatively by considering strings that go inside this spacetime ADS, that fill the inside of this cylinder, and this is once again the statement of ADS CFT. And what you are invited to start playing into today's exercise is to start playing with the metric of this very special spacetime. For example, understand how come I'm claiming that two spacetimes, one is that this spacetime can be the same as this spacetime? How can this be? Furthermore, I told you already once that ADS could be thought as some pseudosphere, some sphere in this two-dimensional higher spacetime. This also doesn't look very much like a pseudosphere. But of course, to understand the geometry of spacetimes, we need to play a bit, understand different coordinates, how different spacetimes look in different coordinates. For different physics, spacetime looks a bit different. And today's tutorial is an invitation for starting to explore the geometry of this spacetime. So of course, it is not about ADS-CFT, it's about this geometry of this spacetime, so that you start getting some familiarity, so that when we get to this geometry by a known as ADS-CFT derivation, quote unquote, because of course it's a conjecture, you will already be a bit familiar with the geometrical aspects of this space. Okay. So let's stop here for today.